So in this problem, we have flow inside a circular pipe. So because the pipe is a cylinder, we need to use Navier-Stokes equations in cylindrical coordinate to find the velocity profile of flow inside the cylindrical pipe. So we are after velocity profile. We want to know if we draw the velocity profile, how does it look like? Does it look like this, for example, or does it look like this, or it has any other shape? So this is actually the velocity profile inside the pipe, which we are after. So as I said, it's obvious because the pipe is a cylinder, we have to use the Navier-Stokes equations in cylindrical coordinate, right? But before getting into the equations, which are actually given in Appendix D of the book, which is page 822, I have to write down all the information given in the problem. So then when we start simplifying that long equation, then it's much, much easier for us if we write down everything up front. So I'm going to read the problem and then write down the meaning of the words that are actually given in the problem statement. So the first thing given in the problem statement is that this flow is incompressible. Incompressible flow. So this is not new. You know the meaning of incompressible flow. That means density is constant and density does not change with respect to anything. Density does not change with respect to time. It doesn't change with respect to space. That's the meaning of incompressible flow. So that means rho, or density, is constant. Or in other words, for example, the variation of density with respect to time is 0, or if you have a term like this, rho Vz, for example, with respect to z, because rho density does not change with z, it's like a constant, you can take it out. We can write down rho, the variation of Vz with respect to z. So this is what we have. So that's the first piece of information given here. So I label this as number 1 because I need to call this later when I simplify the given equation, the Navier-Stokes equation in cylindrical coordinate. Then it also says the flow is fully developed. This is something new. So what does it mean when they say flow is fully developed? A fully developed flow is an axial flow. So that means flow is axial. Meaning that we don't have any velocity in r direction, we don't have any velocity in theta direction. It's just Vz, which is not 0. We just have velocity in z direction, and this is the z-axis, okay? So that's the first meaning of fully developed flow. And then the other meaning is that flow does not change in z direction. So flow does not change in z direction. And that means if, for example, we have in z direction, that means if we have, let's say, a velocity profile here, and we know that that's the velocity profile, and then fluid is flowing in z direction, and then it gets to this point here, this velocity profile here is exactly the same as the velocity profile that we had upstream. There's no change in z direction. Or you can also write it as this. The first derivative with respect to z is equal to 0. So we label these as the second piece of information, and we're going to call it later, okay? Then it says this flow is driven because of a pressure gradient. So there is a pressure gradient, okay? So pressure gradient is not 0. So that's the next thing that we know, that pressure gradient is not 0. This is number 3. And then it says you can neglect gravity. So no gravity. And this is number 4, right? And then let's make an assumption as number 5. And let's assume flow is steady. And make the last assumption. Let's assume flow is symmetric around the axis, or let's assume axial symmetry. Which means there's no variation with theta. So the first derivative with respect to theta is 0. And if you look at the cross section of this pipe, this is the center, this is the theta direction, this direction is the theta direction, and we assume that there is no change when we move in this direction, in the theta direction. Okay, so these are all the given information, and then with these assumptions and these pieces of information, we are ready to go to the Navier-Stokes equation and then write it down, and then we have to start simplifying it using given information. So I write down the Navier-Stokes equation in z direction. It looks like this. We have rho gz, that's the first term. And then the second term is gradient of pressure in z direction. The third term is mu multiplied by 1 over r, the first derivative with respect to r, and then we have r, the first derivative of Vz with respect to r, plus 1 over r squared, second derivative of Vz with respect to theta, and then second derivative of Vz with respect to z. And this equals to rho density multiplied by the first derivative of Vz with respect to time plus, this is the local term of acceleration, and now we have three convective terms, plus Vr, the first derivative of Vz with respect to r, and then plus V theta over r, the first derivative of Vz with respect to theta, and then the last term, which is the last, actually, which is the third convective term, is Vz, the first derivative of Vz with respect to z. Okay, so now I start simplifying this equation using the information given in the problem. So this term is 0, because if I go back to this slide, number 4 is that no gravity. So I assume, obviously, there's no gravity, so the first term is 0. This term is not 0, because if we go back here, number 3 says pressure gradient is not 0. So I have to keep that term, okay? And then let's go inside the three terms standing for the shear stress. So this one is not 0 because Vz actually changes with R. If we go back, we don't have any variation with respect to Z. Number 2, right? Flow is fully developed. So that means there's no variation with respect to Z. And the last one, number 6, it says the variation with respect to theta is also 0. So the variation with respect to theta is 0. The variation with respect to Z is 0. But we have variation with respect to R. So I keep this term. But this one is 0 because there is no variation with respect to theta. So I assume this is 0 because the first derivative with respect to theta is 0. You need to look at number 6. And then this one is also 0 because flow is fully developed. And then the variation with respect to Z is 0. So you need to look at number 2, okay? And then when we go to the right side, flow is steady. So this term is 0. So this is actually our number, if we look at it, this is our number 5, where we assume that flow is steady, so we don't have any variation with respect to time. And then here, VR is 0, because of number 2. If you go back and look at number 2, where it says flow is fully developed, then that means VR and V theta are 0, and we only have VZ because flow is fully developed. So this VR is 0, so the entire term is 0. And then this one is also 0 for the exact same reason, because flow is fully developed, and then we don't have VR and V theta. We just have axial velocity, which is VZ. And then here, this is 0 because, again, flow is fully developed, meaning that flow does not change in Z direction, so variation with respect to Z is 0. And again, you need to look at number 2. If I go back to number 2, you see when I say flow is fully developed, that means flow is axial. So VR and V theta are 0, VZ is not 0. And then flow does not change in Z direction, meaning that the variation of VZ with respect to Z is always 0. And that's why I'm assuming that this term here is 0. So the only two terms which are not 0 are pressure gradient and the first term of shear stress. So we can write them down again. So what we have is the first derivative of pressure with respect to Z, plus viscosity, and then 1 over R, the first derivative with respect to R, the first derivative of VZ with respect to R, equal to 0, right? This is what we have from Navier-Stokes equations. So I'm going to simplify this a little bit, and I'm going to transfer, let's say, this term to the right, the pressure gradient to the right, and then divide it by this viscosity over R to see what we get. So I can say, therefore, so here I can say, therefore, the first derivative with respect to R, and then R, the first derivative of VZ with respect to R is equal to, this goes to the other side, so this negative sign is gone, and then it's like 1 over viscosity, pressure gradient, and then we have R. So obviously now I can take an integral of both sides, and if I do that, so what I get is, if I take an integral, the left side, this first derivative is cancelled by the integral, so I have R, the first derivative of VZ with respect to R, and then on the right side I have 1 over 2 viscosity, pressure gradient, and then R squared. It's actually R squared over 2, and then I wrote the 2 here, okay? Plus integral constant, which is C1, okay? So now I'm going to divide both sides by 1R and write it as the first derivative of VZ with respect to R is equal to 1 over 2 viscosity, pressure gradient, and then this R squared is cancelled by R, and it's just R, plus C1 divided by R. Now we are ready to take the second integral to get to this VZ, which we are after. We are after velocity, the axial velocity, right? So if I take the second integral, then the left side of the equation is just VZ, and then the right side is 1 over 4 viscosity, pressure gradient, and then I have R squared plus ln R, actually it's C1 ln R, because C1 is a constant, and then ln R plus C2. So this is actually the general form of velocity profile, and now we need to use two boundary conditions to find C1 and C2. So the first boundary condition that I'm going to use is this. Say boundary condition 1. When R is 0, that means we are at the center of the pipe, right? We know that velocity is maximum, but it has to be finite. We cannot have an infinite velocity at the center line, right? So I say VZ must be finite. So it cannot be infinite, right? So if I set r to 0, velocity to 0, then vz is equal to, the first term is going to be 0 because it's 0 squared and it's 0. And then the second term is going to be C1, and then we have ln of 0 plus C2, okay? So if this thing, we know that this thing has to be finite, okay? If this thing is supposed to be finite, C1 must be 0. Why? Because this ln of 0 is infinity, okay? And if you want to have this term 0, then C1 must be 0. Otherwise, Vz, which is axial velocity at a center line, is going to be infinity. And we know that this is not physical and this is not actually possible in the real world scenario. So from here, we know that this C1 must be 0. C1 must be 0 because if C1 is anything other than 0, then this term is infinity and the whole Vz is infinite, which is wrong, right? So we know that C1 is 0, and then we are left with this first term and C2. And now I'm going to use the second boundary condition, okay? So I write boundary condition 2. Let's write down the boundary condition. We know if R is equal to capital R, meaning that we are at the surface of the cylindrical tube, then we know that Vz must be 0 because it's at the walls of the pipe and the walls of the pipe does not move. So velocity at a solid wall, velocity of the flow at a solid wall is always equal to the velocity of the solid wall. So this Vz here is equal to 0, okay? So let's write down the, what is it, the equation for velocity, which we got here. So it's like this term, 1 over 4 mu pressure gradient r squared, 1 over 4 mu pressure gradient, and then we have r squared, and then we have C2 and C1 ln r is already 0, okay? So now I'm going to assume that Vz is 0, and then this r is actually equal to the maximum r because we are at the walls, right? So it's 1 over 4 mu pressure gradient in z direction r squared plus C2, and then from here I say C2 is minus 1 over 4 mu pressure gradient, and then we have r squared. So therefore we can say Vz is equal to 1 over 4 viscosity pressure gradient r squared minus, it's actually plus C2 and this is C2, so I write down C2, 1 over 4 viscosity pressure gradient, and then I have capital R squared. So I can take out this 1 over 4 mu and I can say Vz is like 1 over 4 mu pressure gradient in z direction multiplied by r squared minus r squared. And this is actually the total and the final velocity profile in z direction, representing the axial flow. And as you can see, this Vz changes just with r, it doesn't change with z because flow is fully developed, and then it doesn't change in the axial direction. And also it does not change with theta because we assume there is a kind of axial symmetry, and then it doesn't change with theta too. So V is just a function of R. That's what we decided up front, and then we see after we solve it, we find this Vz just a function of R, which obviously makes sense.